Imagine asking a stranger for directions to 23 Church Street. You get exact directions, but now they know exactly where you're going. What if you instead asked, are there any streets here ending in the letter H? You'd get a confusing list, your real destination hidden in the noise. This is the trick Bitcoin's lightweight wallets tried, and why it ultimately failed. Lightweight clients, also called SPV wallets, Simplified Payment Verification, can't store the full blockchain. They need to ask a full node, do you have my transactions? A naive request reveals every address the wallet owns. The tourist's trick has a precise mathematical cousin, the Bloom filter. Picture an array of 16 bits, all set to 0. Pair it with 3 hash functions, deterministic mappings that turn any input into a fixed number. Together, these let a wallet describe what it wants vaguely enough to hide its intent, while still getting useful answers. Let's add a pattern. Take address A, run it through hash function 1. It returns index 2. Hash function 2 returns 7. Hash function 3 returns 13. We flip bits 2, 7, and 13 from 0 to 1. Now add address B. Its hashes point to indices 5, 7, and 11. Notice bit 7 is already on. That's a collision, and the collisions are the whole point. The filter no longer records which address turned on bit 7. It only records that something did. 2 patterns, 6 indices, but only 5 bits flipped. The filter compresses identity into ambiguity, and critically, patterns cannot be removed. Erasing a bit would erase part of every address that touched it. Now testing membership. Query pattern C. Its hashes point to bits 0, 4, and 9. Bit 0 is still 0. We stop immediately. The answer is definitely not present. A single 0 bit guarantees absence. Now query address A again. Bits 2, 7, and 13, all ones. The answer is probably present. Not definitely, because some other pattern's collisions could have flipped those same bits by accident. This is the Bloom filter's signature asymmetry. Definitely no, or maybe yes. Remember those 4 words, they're the entire story. False negatives are impossible. False positives are inherent. And in BIP37, those false positives become a feature, not a bug. The filter is tunable. A larger array with more hash functions is precise. Few false positives, lots of bandwidth saved, but the peer learns almost exactly which addresses you care about. A smaller filter collides more often, returns noise alongside your real transactions, and protects your privacy by ambiguity. This is the tourist asking about streets ending in URCH versus streets ending in just H. More noise, more cover. BIP37 let the wallet pick its own point on this dial. Here's how BIP37 actually wired this in. The client builds a filter from every public key hash, script hash, and the transaction ID it cares about. It sends a filterload message to a peer. The peer scans every incoming transaction, outputs, inputs, signatures, witness data against the filter. When something matches, the peer responds with a merkleblock. The block header plus a Merkle pass proving inclusion, followed by the matching transactions themselves. The wallet verifies the pass and trusts the result. When a new UTXO, an unspent output, appears, the wallet sends filteradd to extend the filter. To start over, filterclear resets it. Remember, patterns can't be deleted, so refining the filter means rebuilding from scratch. Elegant, efficient, and within a few years, effectively dead. Now the failure. A Bloom filter does not encrypt anything, it obfuscates through collision. A malicious full node has the entire blockchain on disk. It can test every address ever used against your filter. Real wallet transactions cluster. An output from one of your transactions becomes the input to the next. Parent and the child linked on the public ledger. False positives, by contrast, are random and isolated. They don't connect to anything. So the attacker takes the set of matches, draws the transaction graph, and watches the noise drop away. The connected component is your wallet. The orphan nodes are the cover. A 2014 paper demonstrated this in practice. Researchers recovered the majority of addresses in real BIP37 filters using nothing but graph analysis. The privacy promise had collapsed. There was a second problem: denial of service. A specially crafted filter, one set to match almost everything, or designed to force expensive script evaluation, could compel a full node to scan and serialize huge volumes of data per block. One small client message, gigabytes of node work. Multiply by thousands of malicious peers, and you have a cheap way to knock honest nodes offline. The protocol gave clients the power to dictate server workload with no rate limiting and no accountability. Bad privacy on one side, denial of service on the other. The combination was fatal. Bitcoin Core's response was gradual but decisive. The filter service was disabled by default, then restricted to allow listed peers only. Today, almost no public node serves BIP37 filters. It's effectively deprecated. The replacement inverted the entire model. BIP157 and 158, compact block filters, flipped who builds what. Now the full node constructs a deterministic filter for every block and publishes it. The wallet downloads filters, checks locally whether anything matches, and only then requests the relevant block. The node learns nothing about which addresses the wallet cares about. Privacy moved from probabilistic obfuscation to architectural separation. The Bloom filter era is a case study in a deeper lesson. Privacy on a public ledger is extraordinarily hard. Probabilistic obfuscation crumbles against adversaries holding the entire chain. Definitely no, maybe yes. The mantra still defines what Bloom filters are good for. But in cryptocurrency, where every transaction is forever visible, every clever shortcut eventually meets a cleverer attacker. BIP37 was elegant. It was not enough.